Morning, everyone. We're a bit early. We'll wait till everybody comes in. How's everybody doing? Questions while we're waiting? No, nothing. We're good. Yes, somebody's pointing out that web work was graded 0. Don't worry about it. First of all, open it, complete it. Don't worry about the grade. I will fix that. As I mentioned, the web work system has been revamped. This was one of the issues in that whole revamping. I'll take care of that. Web work is part of the grade. It counts as 30% of the grade. Yeah. It's really the assignment component. Morning, everyone. Questions while we're waiting? Still a bit early. Let's give it a few more minutes. First of all, tutorials only start next week. You are allowed unlimited attempts on the web work. Benjamin, web work is the assignments. There's a link on my courses already up. Assignment 0 is there. It's a tutorial on how the web work system works. Please go ahead and have a look at it. The web work, there's a link in the links section, I want to say. Although now you're making me doubt that. Pretty sure it's there. Assignment 0 is up. It's not for marks, but it's a tutorial on how the web work system works. Please have a look at that. Monday, as you know, is a holiday. You don't have to attend a different one. You can attend the one on the following Monday. There's no issue. Perhaps you should maybe attend a different one next week. If you wish, that's fine too. Maddie is asking for negative basis for the exponents. I mean, what were they asking you to do there? Because you can evaluate something like -2 cubed, right? There's no issue there. It's when you start taking fractional exponents that you run into some problems. So if they're asking you to evaluate something like this, no issue, you should be able to do that. We do not have a lecture on Monday. Monday is a holiday. So courses will resume, or at least this course will resume next Wednesday. We're doing 1.4 today. We're finishing up 1.4, moving on to, I want to say 1.5. When do we attend the tutorials? An announcement will be made. We still haven't worked out all the details yet, but an announcement will be made on my courses. 7th edition of the book is certainly fine. Well, while we wrote that there, negative 2 cubed, as you know, is should all the review videos from the other prompts be tested, or is it review? It's review material. Thank you, everyone. Thank you. Negative 8. It's review. You're not going to be tested on it per se, but the point is that you need to know it to move forward. It's factoring, it's adding fractions, it's this, it's that. It's stuff that you need to be an expert at in order to do well in this course. Because you don't want to know the stuff we're doing here and yet not know the previous material. And that's going to be an issue if how do we sign into web work? That's the thing. You don't. That's the beauty of what they did this semester. There's no signing in. In the links section under the content tab on my courses, you have a link and it takes you directly to web work. Michael is asking for partial fractions. We're going to do that in this course. This is one of the, well, actually not this course, but 141. This is one of the topics of 141. Well, you are being tested on pre-calculus material on the midterm, but it's really going to focus on exponentials, logarithms, and so on. Those videos that were posted is pre-calculus review. So it's stuff that I'm assuming you know and you're excellent at. Have a look at them, do some exercises, make sure you're comfortable with that material. Web work is only due once a month. I mean, I never announced that, and that's certainly not the case. You should expect to have 5 or 6 web work throughout the semester, so that turns out to be once every 2 weeks, more or less. Yeah. Today is exponentials and logarithms, that's right. As well as stuff in between, right? There's going to be a bridge to go from exponentials to logarithms. Yeah. Then just go to my courses, click on content, and then links, and then you'll have a link to web work. That's it. You should be checking web work regularly. I oftentimes forget to mention a web work has been opened. All right, let's get to work. Last time we were doing stuff from exponentials. Let's do a few more. We're doing stuff from page 52. The question is asking us for a rough graph. Danielle is asking if we have a lecture at 4:30 today. We do not, right? Instead of having this awkward fourth lecture, I decided to break up that hour into 20-minute intervals that we are tacking on to the end of each lecture. So instead of going from 11:30 to 12:30, we're going to go to 12:45, more or less, 3 times a week. So let's look at the graph of this, or let's graph that. Again, it's just a rough graph, right? It's not anything too perfect. Tutorials only start next week. The first assignment 0 is up on web. So let's break this down by starting by looking at the graph of y equals 1/2 to the x. We saw what this looks like, right? This is an exponential function, so it's only one of 2 possibilities, either this or that. And since the base is less than 1, this is the graph of y equals 1/2 to the x. This part right here. If you multiply by 2, what does that do? That doubles the y value for each of these. So it still looks the same. Just twice as high, right? So instead of this being 1, it's now 2. And now what do you want to do? You want to subtract 3. What does that do? That brings everything down by 3. So it used to be a 2. If you bring everything down, it's now -1. And this, which used to be 0, right? The x-axis, y equals 0, if you bring that down, it becomes -3. And there it is. Absolutely. Just a rough graph, but there it is. How are we doing? Let's try another one. This is number 12. Same question, we're asked to graph this. Now you know the graph of y equals 4 to the x. We saw that yesterday. And again, exponential function with a base bigger than 1, so they all look the same. There it is. Now what does this x plus 2 actually do? Well, the way I like to think about it is notice that if x is -2, this is 4 to the 0. So instead of having 4 to the 0 right here, you have 4 to the 0 occurring at -2. So at -2, it's 1. And when x is 1, this used to be 4. But now here, 4 is going to occur when x is -1. And so on and so on. So really, it's this graph, but shifted to the left by 2. So this shifts to the left by 2. In the same way, this shifts to the right by 2, right? When x is 2, the whole thing is 4 to the 0. So this 4 to the 0 would occur at x equals 2. So it's this shifting or translation of the graph to the left or to the right. Let's do one more. Y equals e to the absolute value of x and let's take this time to decompose the absolute value of x in a way that perhaps you have never seen before. Let me ask you this. What is the absolute value of 2? Thank you. Absolute value of 2 is 2. What about absolute value of -3? Absolute value of -3, thank you, Kelly, is 3, which I'm going to conveniently rewrite as -3. So that we can generalize this idea. The absolute value of x, if x is bigger than 0, the absolute value of x is just x itself. Right? If you take a number that's bigger than 0, like 2 or 7, the absolute value of 7 is just itself, namely 7. If x is negative, though, the absolute value of a negative value is negative of itself. So the absolute value of x is -x if x is negative. This is a nice piecewise defined function for the absolute value of x. Consequently, in this case, the absolute e to the absolute value of x is going to be, according to this, e to the x if x is positive, and e to the negative x, if x is negative. What is a piecewise defined function? Well, as the word suggests, it's a function which is defined in pieces. So it's this piece if whatever, in this case, x is bigger than 0, or it's this piece if, in this case, x is less than 0. All right. Can we explain the minus x again? Observe. We suggested that the absolute value of negative 3 was 3. You claimed that, and it's correct. And what I did was rewrite it as negative 3. So if your number is less than 0, like negative 3 is, the absolute value of negative 3 is negative of itself, negative of negative 3. So by rewriting absolute value of x as a piecewise defined function, right? And you know, I mean, do we want to convince ourselves here? What is the absolute value of 17? According to this, 17 is bigger than 0. So the absolute value of 17 is just 17. Again, using this, absolute value of negative 6. Negative 6 is a negative number. It's a number that is less than 0. So this is the rule we're using. So absolute value of negative 6 is negative 6, which is 6, exactly as you would expect. All right. So now we're able to graph. Right, the graph of e to the x, an exponential function, where the base, Euler's number, 2.71, 82, 81, 82 and stuff, is bigger than 1. So you know what that looks like. Looks like this. And then y equals e to the negative x, which is really, right, negative exponent. So 1 over e to the x, or 1 over e to the x. Again, an exponential function where the base is somewhere between 1/2 and 1/3, so less than 1. And so looks something like this. And now we want to put the two together, right? Because this function is made up of these two pieces. So it's pieces of these two graphs. Let's put everything together. Let's put everything together. It's the graph of e to the x if x is bigger than 0. So in this region, in this part of the plane, it's that graph. And for values less than 0, right here, it's this graph, which coincides exactly at this point here. And there it is. Very nice. How are we doing here? Questions? Well, I mean, perhaps you're asking yourself, who cares about exponential functions? And the answer is everybody. This is not considered a parabola. And once we do some more work, once we get further into the whole knowledge of calculus, you'll understand that something fishy is happening here. I don't want to spoil it for you, but yeah. Well, let me say this. Once we define the derivative, well, it's not that it's undefined. F of 0 actually is defined, and it's 1. And it's actually continuous. Well, it is continuous. Again, we have not defined that term, but I can draw the picture without lifting the chalk from the chalkboard. So it is continuous, but it is not differentiable. Exactly, Victoria, very nice. But that remains to be proven, and we have not defined those terms yet. But once we do, you can come back to this example and convince yourselves. Absolutely. But I was going to discuss the reason exponential functions are important. Consider the following scenario. Suppose you have $1,000 in the bank. And suppose that through some investments that you made a while back, because the interest rates are not that high anymore, but suppose that you had this money earning 8% interest per year. April is asking, how do we tell if something is piecewise? If it's written in a way that the function is made up of different pieces, right? So it says in the word piecewise, different pieces. That's all it is. Right, so suppose you have $1,000 in the bank earning an 8% annual yield, and you leave that money in the bank for a year. How much money will you have at the end of the year? Right. Very easy to calculate, and I'm sure you know exactly what it is, right? You'll at the end of the year, after 1 year, you'll have your $1,000, and then you'll have the interest on that $1,000. Right? You'll have that interest on $1,000, which is $80. You'll have $1,080. Absolutely. No ambiguity there. Nothing fancy is going on. And then yeah, right, exactly. assuming no market crash. But here the assumption is that these were investments you made long ago, and it's in the bank, so no worries there. That's after 1 year. What about after the second year? Well, now keep in mind, after the first year, you now have 1,080. Compounded interest, absolutely, right? Because at the end of the first year, you now have 1,080 in the bank. So at the end of the second year, you'll have that 1,080 plus the interest on that 1,080. Right? We'll go with JD's figure there, 1166 and 40. I'll believe it. But what I want to bring to your attention is if you factor out 1,000 from here, you get a 1 plus 0.08, or 1,000 times 1.08. And here, if you factor out 1,080, you get 1 plus 0.08, or 1,080 times 1.08. But the 1,080 was 1,000 times 1.08. So this is really 1,000, 1.08 times 1.08, or 1,000, 1.08 squared. And you can continue on in this fashion, right? After 1 year, it's 1,000, 1.08 to the 1. After 2 years, it's 1,000, 1.08 squared. And you can generalize easily. You see what's happening. And after n years, it's 1,000, 1.08 to the power n. Absolutely. And you can generalize that, of course, and you get the idea of an accumulated value if you place an amount A in the bank at interest rate I, compounded once per year for n years, this is how much money you'll have in the bank after n years. So you see you have this exponential function here, 1.08 to the n, or 1.08 to the power x. Yes, Benjamin, that's correct. So it's to motivate the importance of the exponential function, right? Everybody wants to make money. Exponential function. What about when you compound, when the compounding is twice a year? Well, absolutely, right? I mean, that certainly comes into play. And what if it's 3 times a year, 5 times a year, 10 times a year, 100, 1,000? These are all excellent questions. And what if you took a limiting case here? What if the interest was compounded continuously? It's a very interesting question. Maybe we'll answer it later. Maybe. Yeah, exactly right. Rise in COVID cases also is exponential. There's this thing they call the R factor. I think they changed the name this week, but 1 being the important factor. If R is less than 1, then the number of cases is going down. If R is bigger than 1, then the number of cases is going up. I mean, there's all of this. Yeah, exactly. All right. Let's move on. Let's move on to something different. Consider the function 2x plus 1. You're familiar with this function. You've seen this before. Let's just plug in a few values just for fun, but I know that you know what's happening here. F of 0. F of 0 is 1. I mean, no surprises there. F of 1. F of 1 is 3. F of negative 1/2. Is 0. F of 2 is 5, and so on and so on. Right? I mean, you know what the graph of this function looks like. It's just a straight line. Nothing. Nothing special is happening here. Where I want to go with this is, do we know a function where if you plug 1 in, you get 0 back? If you plug 3 in, you get 1 back. If you plug 0 in, you get negative 1/2 back. If you plug 5 in, you get 2 back. Exactly, right? I'm asking, what is the inverse of this function? And what is the inverse of this function? What function is such that when you plug 1 in, you get 0? When you plug 3 in, you get 1. When you plug 0 in, you get negative 1/2. I'm getting different answers. Somebody's suggesting x minus 1 over 2. I think that works. Let's check. If you plug 1 in, 1 minus 1 is 0. Looking good. 3 minus 1 is 2. 2 over 2 is 1. Looking very good. When you plug 0 in, you get negative 1/2. When you plug 5 in, 5 minus 1 is 4, divided by 2 is 2. There it is. Very nice. Let's try another one. One over x minus 1. Guillaume is asking for the fastest way to find the inverse. So an excellent question. Before we do that, let's just try another one. But Andre has given us the answer there. F of 0 is negative 1. F of 2 If we plug 2 in for x, we get if we plug 3 in for x, we get 1/2. If we plug in 1/2, what happens if we plug in 1/2? Can we do that in our heads? Anyone? -2, thank you, JR. And so on and so on. The inverse function is a function such that if you plug -1 in, you get 0 back. If you plug in 1, you get 2 back. If you plug in 1/2, you get 3 back. If you plug in -2, you get 1/2 back. What is this function? What is the inverse function here? 1/x plus 1. Sounds promising. Let's check. If you plug in -1, you get -1 plus 1 is 0. Very nice. If you plug in 1, you get 1 plus 1 is 2. If you plug in 1/2, 1/1/2, you know it flips, and that gives you 2. Plus 1 is 3. Very nice. If you plug in -2, you get -1/2. Plus 1 is 1/2. Very nice. Very nice. This leads us to the following definition. F of x and g of x are said to be inverse functions of each other if, that's exactly where we're going. We're going to introduce that notation. If what? What had we said? I rubbed it off now, but we had f of -1/2 was 0. So if you plug in 0, you get the -1/2 back. Here, f of 2 was 5. So that if you plug 5 in, you get the 2 back, right? If you plug 0 in, you get 1. So -1. So if you plug -1 in, you get 0 back, right? So you plug in the next value, you get some y. And then you plug in that y value and you get the x back. What are we saying? We're saying that if you compose the two, you get x back. Exactly that. Rachel, you want to be careful. You want to be careful with what you wrote down there. But let me finish up with this definition. In this case, we say g of x is the inverse of f of x, and we denote g of x as f inverse of x. Be careful with this notation. f to the negative 1 here does not mean 1 over f. No one uses that notation to mean 1 over f. It's notation for the inverse function. And let's verify with our previous examples. We started with the function 2x plus 1, and somebody suggested that the inverse was x minus 1 over 2. Let's verify that this is correct by taking the composition. Correct, Benjamin. Right? F inverse can be thought of as doing the opposite operations of f in the reverse order. Right? Here you're multiplying by 2 and adding 1. Here we're going to subtract 1 and divide by 2. Very nice. But now this is the proposed inverse. Let's prove it using the definition. We want to make sure that these two things are satisfied. So let's look at the composition. F of f inverse. What is that? F inverse is proposed to be x minus 1 over 2. So everywhere you see an x in your function f, you're replaced with x minus 1 over 2. Everywhere you see an x in your function f, you're replaced with x minus 1 over 2. So this is 2 times x minus 1 over 2 plus 1. The 2's cancel out nicely, leaving you with an x minus 1 plus 1, which is just x. Exactly as expected. Let's do the other way around. F inverse of f. F of x is 2x plus 1. Everywhere you see an x in your function f inverse, you're replaced with 2x plus 1. So that is 2x plus 1 minus 1 over 2. If you open up the brackets, the minus 1's cancel. Well, the 1 and minus 1 cancel, leaving you with a 2x over 2. The 2's cancel, leaving you with x exactly as expected. Benjamin is asking, why does this give us x? Well, think about what we were doing. Think about what we were doing with the function and its inverse. Right? F of x is 2x plus 1. We suggested the inverse was x minus 1 over 2. You know, we had plugged in some values here. When you plug in 0, you get 1. The inverse function was built so that if you plug 1 in, you get 0 back. But 1 was f of 0. So this is f inverse of f of 0, and we're getting 0. Right? This 1 is f of 0. So if you plug in 0, right, any value of x, you should get that x back. Is one composition sufficient proof? Theoretically, let's say no. Let's say no. No. You should always check both. Now the question has arisen, how do you find the inverse? And really the answer comes from, what are we doing here? We were plugging in an x value, getting a y, and then plugging in the y value into the inverse, getting the x back. So we're really switching the role of x and y, and that's how you find the inverse. By switching the role of x and y. Let's take our first example, where we had 2x plus 1. Switch x and y and solve for y. So if you switch x and y, you have x equals 2y plus 1, and then solve for y. So bring the 1 to the other side, and then divide by 2. There it is, exactly the inverse. It is very straightforward, absolutely. Let's consider the other example we looked at. One over x minus 1, right? We had already come up with the inverse, but let's do it now, not knowing. If we interchange x and y, we have x equals 1 over y minus 1. And now solve for y. Solve for y by cross multiplying, which is, by the way, well, I mean, let me not get into that quite yet. Let's cross multiply. And then bring the 1 to the other side. There it is. Exactly the inverse that was suggested. Had we checked that this was the inverse? I think we hadn't. Why don't we check? If f of x is 1 over x minus 1, the proposed inverse is 1 over x plus 1. Let's look at the composition. F of f inverse. F inverse is proposed to be 1 over x plus 1. So everywhere you see an x in your function f, you replace with 1 over x plus 1. So everywhere you see an x, you replace with 1 over x plus 1. Open up the brackets. The 1's cancel out nicely, leaving you with 1 over x. And you see what's happening here, right? This is 1 divided by 1 over x. And when you divide by a fraction, It's like multiplying by the reciprocal, which is just x, exactly as expected. While we're here, it's a nice exercise to do the other composition, might as well, for completeness, right? F inverse of f. Your function f is 1 over x minus 1. So everywhere we see an x in f inverse, we're replaced with 1 over x minus 1. So here's the x. So that's 1 over x minus 1 plus 1. You're divided by a fraction again, so you multiply by the reciprocal. And this becomes x minus 1 plus 1, which is easily seen to be x. Questions here? How are we doing? How are we doing with inverse functions? Well, here's a question to you. Do all functions have inverses? It's a valid question. Let's take an example. F of x equals x squared. What is f of 1? F of 1 is 1. F of 1 half, you know what that is. 1 quarter. F of 0 is 0. F of minus 1 squared is 1. So the inverse would be a function such that if you plug 1 in, you get 1 back. If you plug 1 quarter in, you get 1 half back. If you plug 0 in, you get 0 back. If you plug 1 in, you get minus 1 back. And here's the issue. If you plug 1 in, you get 1 back. But if you plug 1 in, you get minus 1 back. And now we're in trouble. Now we're in trouble because this is no longer a function. If you plug 1 in, you get 1, or do you get negative 1? There's ambiguity. This is not a function, and that's the problem. That's the problem. What is the problem? The problem is you don't want two different values of x giving you the same y value. Because then you're not going to be able to go backwards. Does everybody see that? If you have two different values of x giving rise to the same y value, you're going to have a problem going back. Is 1 going to give 1, or is it going to give negative 1? That's the problem. So that's the issue. That's the issue we're going to want to stay away from. Let's introduce a definition. A function f of x is said to be injective or one-to-one sometimes denoted one-to-one like this. So a function is said to be injective if whenever f of a is equal to f of b, then a is equal to b. Noah's asking for a function to have an inverse. Does it have to be a one-to-one? That's exactly where we're going. Absolutely. For a function to have an inverse, it has to be one-to-one. And moreover, if a function is one-to-one, then it has an inverse. So if it's an if and only if statement. Jennifer is asking, what do I mean by one-to-one? Exactly this. This is the definition of one-to-one. I'm giving you the definition right now. It's a brand new definition. Most of you have never seen this before. There it is. If whenever f of a is equal to f of b, then a is equal to b. Let's take a few examples. Let's consider the first function we considered today. We are on 1.5, absolutely. Consider this. Here's my question. Is this one-to-one? Exactly as Willem is suggesting, we're saying that there are no two. That's actually not exactly it. Not two y values for every x, but rather the only way you get two y values to be the same is if the x values were the same to begin with. The y values cannot repeat. Exactly that. So is this function one-to-one? Let's check. Function is one-to-one if whenever this is true, this has to follow. So let's assume f of a is equal to f of b. What does it mean in this case? Well, f of x is this. So what is f of a? Everywhere you see an x, you replace with a. F of a is, you know what it is. Two a plus 1. What about f of b? Everywhere you see an x, you replace with b. F of b is 2b plus 1, thank you. Bring this one to the other side. It's going to cancel. And we're left with 2a is equal to 2b. Divide both sides by 2. And you get a equals b. So if f of a is equal to f of b, then a is equal to b. I.e. your function is injective. Let's try it with this one. 1 over x minus 1. Is this? Matthew is asking me to define injective. I've done so right here. This is the definition of injective. Whenever f of a is equal to f of b, then a is equal to b. Injective means one-to-one. Moments. Apparently there's an issue with the video. Tell me when it's back. Is it back now? Still issues. So many issues. Back? It's back? Yes? Kayla? Excellent. Very good. We didn't do anything. You didn't miss anything. So it's all good. Is it always around this time? Yeah, we'll have to keep track of that. All right. So we're assuming f of a is equal to f of b. We're hoping, or well, I mean, the question is, does it necessarily follow that a is equal to b? F of a, and where you've seen x in your function, you replace with a. So this is 1 over a minus 1. F of b, everywhere you've seen x in your function, replace with b, 1 over b minus 1. The definition in the book does refer to the y coordinate, absolutely. Right, so we have this. Let's cross multiply. Let's cross multiply and we get b minus 1 is equal to a minus 1. Bring the minus 1 to the other side. It becomes a positive 1. And we get b equals a. There it is. How are we doing? So once again, the function is 1-to-1. Well, now, I mean, the question arises naturally. It seems that you could always do that. Isn't every single function 1-to-1? Isn't every single function injective? And the answer, of course, is no. As this simple example shows you, if you take x squared, g of 1 is 1. And g of negative 1 is also 1. So g of 1 is equal to g of negative 1. But, right? So g of a is equal to g of b, but a is not equal to b. You've displayed two x values which give rise to the same y value. Not possible for an injective function. And I mean, you know what kind of function this is, right? You know it's a parabola. You know its graph. And the problem is that there exist two different x values giving rise to the same y value. I've chosen one here, but of course if you go with 2 and minus 2, it's the same problem, and 3 and minus 3, and really any positive number and it's negative is an issue. So, yeah. And the one-to-oneness, the injectiveness, you want to make sure that no two different x values give rise to the same y value. In other words, that no horizontal line crosses the graph more than once. This is known as the horizontal line test. Let's state it. Very similar to the vertical line test when you're testing if it's a function or not. Exactly. The function f of x is injective if and only if every horizontal line crosses the graph of y equals f of x at most once. So very similar to a vertical line test when you're testing for functions, right? Any vertical line can only cross at most once, otherwise it's not a function. Here, every horizontal line can cross at most once, otherwise it's not injective. So this function here is not injective. X squared is not injective. However, if you did restrict the domain, right, this function is not injective on the whole domain R. But if you restrict your attention to half of it, either the positive half or the negative half, right? So either this half or that half, then it is injective, right? Every horizontal line is going to cross at most once. Here, horizontal lines don't cross at all. Same thing here. So both of these pieces are injective. And well, I mean, now we want to relate that to inverses. Let's do so via the following theorem that I offer without proof. A function is invertible if and only if it is injective. So a function is invertible, or a function has an inverse, if and only if it is injective. So this injectivity property is an important one. It guarantees. So any function that is not injective does not have an inverse, correct? Unless you restrict the domain and make it injective. Absolutely. Absolutely. Let's go back to this example, if you will, right? Y equals x squared. If we were looking for the inverse, you would interchange the x and the y, and you would solve for y. And how do you solve for y? You're going to take the square root of both sides, and you have the plus or minus square root of x. Now, that's a problem, right? Because plus or minus gives you two possibilities. So in general, your function is not injective. But if you restricted your attention to one of these halves, this would correspond to the positive square root. If you restricted your attention to this function, then the inverse would be the negative square root. And there it is. How are we doing? Well, now the question arises naturally. Consider the function y equals 2 to the x. We've been looking at that. You know the graph of this function, right? This is an exponential function. Base is bigger than 2, bigger than 1. So this is the graph. An invertible function is a function that has an inverse. So here's the graph of y equals 2 to the x. And what do we notice? By the horizontal line test, this function is 1 to 1. Right? By the horizontal line test, this function is 1 to 1. So by this theorem, this function is invertible. This function has an inverse. So 2 to the x is 1 to 1. So this has an inverse. How do we find the inverse? We interchange x and y, and we solve for y. However, it's impossible to do that now, using the techniques we've seen so far. But we know this function has an inverse. We know this function has an inverse. So we define it. We cannot solve for it, but we define it. And as is pointed out, we call it the logarithm. The logarithm is the inverse function of the exponential. We know it exists because the exponential is 1 to 1, so it has to have an inverse. We cannot solve for it, so we define it, we give it a name, and call it the logarithm. And there it is. It's a good place to end for the day. We'll pick this up again on Wednesday, and we'll go from there. Questions in the meantime? How are we doing here? If you want to show something is not injective, April, all you need is an example. So a counterexample does the trick, that's it. Excellent, very good. So you guys have a good weekend. What page should you do for homework? Yes, we didn't get to exercises yet, but let's call it section 11.5. You can have a look at a few things from there. So 11.5, or I mean, it's just after if you're picking up a different book. Last time we were doing exponentials, so here it's leading up to logarithms. Depending on which book you're using, this injective business and inverses may or may not appear, but 11.5 as far as we're concerned, yes. 11.5. Oh, sorry. Yeah, no, I did not mean 11.5. Sorry, I meant 1.5. Thank you. I was I don't know what I was talking about there. Section 1.5. Thank you. 11.5 would have been the other class I'm teaching. Sorry for the confusion there. 1.5. 1.5. Yeah. JR is asking for x squared. How would you describe its inverse? Well, in general, you would say it's not invertible. It does not have an inverse. However, if you restrict your attention, if you split up the domain appropriately, then you may be able to define an inverse. We do not have a second lecture today. As I mentioned on the announcement, instead of having an awkward fourth lecture at 4:30 or whatever, we are extending the 3 lectures, the 3 Monday, Wednesday, Friday lectures. Instead of stopping at 12:30, we go a bit beyond, and that will compensate for having no Friday afternoon lecture. Tutorials start only next week. Grace, there are no quizzes in this class. The term injective is used to define the function, but also the inverse function has to be injective as well, right? By this theorem. So both actually have to be injective. I mean, Anna, it's always okay for you to attend any tutorial you want. They will essentially cover all the same material anyways. No worries. Web work is whenever I upload something. I don't have a set schedule. Is there an example where the inverse wouldn't be injective? That's impossible, right, by this theorem. Because the inverse of the inverse has to be the original function. So, absolutely. If the function is injective, then the inverse exists, and it automatically makes the inverse injective as well, since the inverse is invertible, because the inverse of the inverse is the original function. Are all profs for 139 extending their lectures? There's only one other prof, right? That's Alyssa, and she is not. You're going to have another web work due before September 30th. This is the web work that's up right now is just a tutorial. It's not for marks. So it's just for you to get started with the web work system. Yes, You can, of course, download a PDF for the web work, but that's not, I mean, look, you can do that, that's no problem if you want to work on the problems separately. But in order to submit your web work, you need to click on every individual question, not in the downloaded PDF. Click on every question, and then there'll appear space where you can answer the questions. I will be having office hours at some point, not right now because I'm swamped with other classes and other duties that I have to do, but they're coming. Web work is in the content section under links. Thank you, Kayla. All right. If there are no other questions, I'll see you guys on Wednesday. Have a good weekend. I'm going to post this video soon.